This problem is one that appeared on an AP exam several years ago. Most people were able to get Part A, but didn't know what to do in Part B. The setup of the problem is to use our method of putting all of the information in a drawing, then writing given and find, then the equations, and then the derivative of the equations, and then solving. So let's start out with the work here. And by the way, this work was done by Chloe, who did an outstanding job. What we've got in the given information is that up here, and I eliminated what was irrelevant, we have this information about homework, got rid of it, it doesn't apply. But they did tell us that there was a pipe, and that pipe was flowing a liquid into the trough at a constant rate. So I just said the constant is dV dt, and we don't have a number for that. Now the other thing we know is that volume is given to us as half the base times height times length. So here's the base, small b, there's the height, and then the length, which is, by the way, a constant right there. So then we took that information and we had to write down what we had to find, which is dV dt. The given is already right here. So the next step was to write down the equations that we would need out of this information. And actually, we already wrote it once. But now we're going to put in the constants. So we have volume equals 1/2, and the small b and the small h on our fluid level is going to change, because as the fluid rises, this base gets longer and this height gets higher. The only thing that stays constant is this particular length, which we know is 15. So we put the 15 in as a constant. Remember, constants always go in before you derive. And now we have 1/2 times 15, or 15 halves, but we've got two variables here, and we only want one. So if we look at the relationship right here between the big triangle and the small one, we can see that they're similar triangles, because we have two parallel lines, and this is going to be a case of angle, 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 if you remember your geometry. So we redrew over here the triangles, and we made the relationship that this small b right here, which is our b here, compared to this small h right there, which is just for the smallest triangle, h, is similar to or equal to 5 to 8 of the big triangle. What that allows us to do is isolate one of these variables. The easiest one to isolate is b, so we move the h over, and we take that b value, and we're going to put it in right there for b. And when we do, we have 5/8 h. Now we have one variable, multiply as needed, and you get 75 over 16 h squared. At this point, we're ready to derive, which is the next step. So we're going to write down the thing we want, which is dV dt, and we're going to say that it's equal to the derivative of this expression here. Remember, though, it is with respect to t. Don't mistakenly put a dx there. So we end up with 75 over 16 2h. Now, one thing that is not written here that should have been is we should have finished with dh dt because of implicit differentiation. But we did have it down here. She caught it there. And so dV dt, when you multiply, is this expression right here. Now we're going to figure out what dV dt is, because we're actually given the dH dt. That was given right up here, 2 meters per minute. The height is increasing. And we also know the height. And so we're going to put in 150 over 16. The height when this rate is 2 meters per minute is 4 meters. That's the when. So we're going to put in the 4 meters high, the 2 meters per minute there. And when we multiply it all out, we end up with 75. Now be careful here that you get the right units. This is change in volume over change in time. And volume is always expressed as a quantity cubed. So it's meters cubed. And then the time is just minutes. To do the second problem, we're going to remember that the derivative is going to be equal to 75 meters cubed. And we're going to use that to solve the next problem. When they ask how long it'll take to fill the tank, that implies the entire tank. So we write out the formula of the tank, volume, and we already know what the base, height, and length are because they're in our drawing as 15, 8, and 5 for the whole tank. 300 meters cubed is the volume of the tank. What we also know is that 300 meters cubed is strictly the volume, but we know as well what dV dt is right here. So if we recall that rate times time gives you quantity, which is our volume, then we can use that quantity right here, which we know is going to be for the entire tank, and that's going to be 300 meters cubed. And we know our rate, which we found in the previous problem of dV dt, the rate of the volume that is increasing, 75 right there. The only thing we don't know is t. So we can now isolate t, and when we do, keeping our units straight, we know they have to be 4 minutes.